Computer audio. Start video. Ashley is here with us. Okay, this is Wednesday, October 7th. And so far we just have Ashley and Ryan. We got Ryan. Ryan and Ashley, and that's it. But that's good. Do you have any questions for me before class? We've got 3 minutes. If you have any questions, you may ask them. There's a thing here called chat. I don't see anything on chat. Oh, we've got Mark. We've got Ashley, Mark, and Ryan so far. We're building our class. All right. So we don't have any questions yet. Supposed to be another beautiful day, I think. Ooh, oh, maybe a little more sleep would have been nice. What are we going to study today? Well, we're going to have a test next week over chapters. Let me write that on the board. That'd be good to know. Over chapters 13, 14, and 15. You probably should start on 15. Your test it's exam 2. It's on chapters 13, 14, 15. We'll start on 15 here in a little bit. Now that's going to be available a week from today, and it will be due that Saturday. So, well, what is a week from today? Would that be the 14th? 7 plus 7 is 14, right? And let's see, yeah. I think that's right. Yeah. It'll be available a week from today. It'll be due the Saturday. The 17th. Of October. Is Saturday the 17th? Let me look at my calendar here. Yes, it is. Saturday the 17th. Okay. Well, we'll start on 15 here in a little bit. All right. I've got 9:30. It's time for class to start. So let's get started. Let's have a quick review of stuff we know and stuff we've studied in this chapter or in this course. What is this, October? We started in August, didn't we? Are you aware that there are 4 basic tools that we use to solve problems in dynamics? There's 4 basic tools. You might call them methods of solving problems. Instead of tools, you could call them methods. Of solving dynamics problems. We started off in August, and we studied kinematics. Well, we're doing a little review here. Now, kinematics was the study of motion. Pretty much the things you studied there were time, distance, velocity, and acceleration. And that's pretty much it. And that was chapter 12. That was chapter 12. And then the second tool that we studied was Newton's second law. That's chapter 13. I'm looking in the book here. Chapter 13. What do they call chapter 13? They call it kinetics. That's their fancy word, kinetics. See, kinematics is the study of motion, but kinetics involves forces. And Newton's second law deals with the sum of the forces on a body. And then that was chapter 13. Yeah. And then the third tool that we learned about was work energy. Work energy. And that was chapter 14. Let me see what they call chapter 14 here, just a minute. Chapter 4. Well, the name of it is, well, they call it Kinetics of a Particle, Work, and Energy. Chapter 13, they call that Kinetics of a Particle, Force, and Acceleration. So both of these chapters are on kinetics. Which, if you needed to know what that word means, it deals with force. Whereas this chapter here is about force and acceleration, and this chapter here is about work and energy, but you can't have work without a force. So they're both dealing with force, but a little different way of looking at it. And then chapter 4, which the method 4 is called impulse momentum. That we'll talk about that here today. It's another method, another way of solving problems. And what's interesting is you can solve problems with different ones. You can solve a problem with impulse momentum, or the same problem with work energy, or the same problem with Newton's second law. And sometimes you have to use kinematics in order to solve the problem. But those are our 4 methods. And that's it. And then now here's the thing, though. All of this is dealing with particles. We haven't gotten on to, we haven't started studying solid bodies yet, but that's next. That's next. And what we're going to do is we're going to start all over in chapter 15. No, chapter 16. See, this is chapter 15. But when we get to chapter 16, you know what they do? They start all over again, and they study kinematics of solid bodies. Not particles anymore, but solid bodies. See, a particle is just a little itty-bitty thing, but a solid body, it has area, volume. It can rotate and have energy of rotation. And then we study Newton's second law for solid bodies. I forget which chapter that is. We could go down there, and this is where we're headed. And then we studied work energy for solid bodies. And the last thing we'll study is the impulse momentum method for solid bodies. And then it'll be over. It'll be December something, and class will be over. Okay. Well, we'll start working some problems now. Let me go ahead and tell you about this impulse momentum method, and then we'll solve some problems using these different tools strictly with particles. We haven't got to solid bodies yet. After all of this, after we study all of this, we study solid bodies. Do you have any questions? Okay, well, it's always nice to know what we're going to study and what we're doing, and that there is a test coming up. And you do have some homework. Well, let me erase this, and we're going to study this fourth tool or method called the impulse momentum method. And then we'll work some problems, and maybe we could do it different ways. Maybe we could use the Newton's second law to solve a problem. That'd be fun. Or work energy, that'd be good too. Okay, now we're going to tell you about wait a minute, the homework. Let me tell you about the homework so you won't forget. I'm probably going to get behind on my grading, but I'll get with it and grade all your homework. Let's see, today is the October 7th, and your homework is, this is homework number 15. Homework number 15. And the homework is F14.9. It's on page 208. And 1470 on page 224. And it's due, today's Wednesday, it's due the 10th. I believe that's Saturday. Let me look and see. Yep, it's due Saturday. Saturday, the 10th of October. Okay, well, there's your homework, and you probably already knew that. Any comments or questions on anything so far?
Is it F14.9 or just 14.9 or problem 14.9?
I think it's F14.9. Let's look on page 208 and be sure, shall we? Let's see, page 208. We don't want to foul up here. Page 208, it's F14.9. You'll see it there on page 208.
Okay.
But thank you for asking. Now who was that?
Ashley?
Thank you, Ashley. All right, now, what about this one? 224. Let me see if I can find that. 224. And that one's 1470. Yeah, I see it there. I might could help you with that one a little bit. Let me give you a little help on this 1470. I don't want to wreck all your fun, but it might be nice. See, what you have here is a, we're going to talk about 1470 for just a minute, and then we're going to talk about impulse momentum. You've got a 15-pound ball on a 3-foot rod. Here's the rod. Here's the 15-pound ball. 3-foot rod. There you go. Now you know what's going to happen. This thing is going to rotate. It's going to rotate, and it'll be in different positions. Now, see, right now, there's two forces on that rod. There's the weight of the rod, which is 15 pounds. And there's a compressive force of the rod acting on it. I don't really call it a normal force because a normal force implies you have a surface. There's not really a surface. That ball is not on a surface. It's connected to a rod, and the rod has a compressive force of, right now it'd be 15 pounds as it just sits there. But it's going to start moving, and it's going to come down here. Now when it's, I'll draw it when it's in different positions here. See, when it's like this, see when it's like that, it's moving. It's got a velocity. See here, there's no velocity. You're going to have to give it a itsy bitsy little tiny push to get it going, but then it starts picking up speed. I maybe made that a little too long. I don't know. Maybe a tad too long. But see, it's gonna pick up speed. Now it still has weight. That hasn't changed any. It's still 15 pounds. But now the rod is pushing on it, and I don't think it's pushing 15 pounds anymore. In fact, I think it's less than 15 pounds. But that's the only two forces on it. Now, a little later, here it comes, it'll be like this. A little later on, it'll be more like that. There's your 15-pound ball there. And that hadn't changed any. It's still 15 pounds. But now the rod's a two-force member, so it can only only push. But it's probably not pushing very much at all, because if this thing, it's going faster now, you understand? The velocity is picking up. When the velocity gets fast enough, that rod, instead of pushing, is going to pull. Here, let me show you that. When it gets somewhere in here, when this rod is like this, there's your 15 pounds. You still got the 15 pounds, but the velocity is really picking up now. See, it's going faster and faster and faster. And what happens when it gets going fast enough is there's a tension. Instead of compression in the rod, there's tension in the rod. It's kind of like if you swing a ball on a chain. Get a ball on a chain and just swing it around and around. There's tension in the chain. And there'll be tension in this rod as this thing gets going fast enough. Now notice in here, there's compression in the rod, and the rod is pushing on the ball. But there is a place where the ball's going so fast that there's tension in the rod. Well, there's got to be a place in between where there is no tension or compression. And that's what they want you to find. I won't tell you any more, that'll spoil your fun. That's part of your homework, but I helped you a little bit. Did anybody have a question on that? Okay, well, I tried to help you on this problem here. It was a little bit tricky. But that's how you do these problems. You draw the free body diagram, and then you put the red stuff on there. Oops, I forgot the green stuff, didn't I? Well, see, here, this would be your tangential unit vector, and this would be your normal unit vector. And the same here and here, but they change. See, the tangential unit vector and the normal unit vector have changed a little bit. And here they've changed some more. Look, here's your tangential unit vector. And there's your normal unit vector. That's how you do these problems. You draw the free body diagram, you put the red stuff, you put the green stuff, and then you write your equations. What equations? Well, in this chapter here that we're studying, this is a work and energy chapter, so you would write maybe the work energy theorem or the second law of thermodynamics, going back a chapter, either one. And you try to solve for that spot where there's no normal force, not normal force, compression or tension force acting on the ball. Any comments or questions? All right, well, let's talk about, I gave you a review. I told you our 4 tools. If you have trouble doing a problem, you probably aren't using one of those 4 tools that you need. Make a little list of your 4 tools and just try each one on your problem. Maybe you'll get lucky. Okay, now right now the topic is, it's really chapter 15. And it's impulse momentum is the name of it. Now the equation, here's how the equation goes, and I want to show you where it comes from, okay? We're going to show you where this equation comes from. That's it. You're looking at the impulse momentum equation. Now this term right here is called impulse. It's got a name. It's the sum of the impulses, but this integral here is called impulse. And you can see the units would be newtons times seconds. These terms here are called momentum. This is your final momentum. And that is your initial momentum. Now the plural of momentum is momenta. The singular is momentum. The plural is momenta. It's kind of like, I know you've seen the word data. Did you know that's plural and the singular is datum? See, datum is singular and data is plural. Anybody ever watch, I believe it's Star Trek? There's a guy on there named Data. Am I right? Somebody correct me. Is that Star Trek that has Data on there?
That is, yes.
Yeah. On Star Trek, there's a guy named Data. He's a robot. But see, he's not singular. I guess he's got a whole bunch of programs, okay? He's plural. That's why they call him Data. They don't call him datum. They call him data. Well, momentum is singular. That's your final momentum, and that's your initial momentum. But if you have several, you would say several momenta, because that's plural. Okay, let me show you where this comes from. Like everything else in this class, it comes from Newton's second law. Newton's second law is the most important equation in our course, and it goes like this. It's just that we're going to write this like this. That's the definition of acceleration, you know, is the first derivative with respect to time of velocity. So I'm hoping that you're all with me so far. Now check this out. I'm going to do a little algebra trick here. See if you can get to here. Can you get from here to here? Can you make it? Okay, now watch this. We're going to do a little calculus trick now. We're almost done. We're going to have this impulse momentum equation here in just a jiffy. I'm going to go like that. That's legal. Ask your math teacher. Now here we're going to do a cute little trick. See, this is the integration of a sum. Did you know that integration and summation are commutative? You can switch them and take the sum of the integration. Am I doing this right? Just a minute now. Yeah, I think I am. See how I switched those two? Did you know they're, the word I think is commutative. Commutative? Commutative? I can't pronounce it. It's just like multiplication. See, 5 times 3 is equal to 3 times 5. You can switch them. And the same thing here with integration and summation. If you don't believe me, go ask your math teacher. Now we're going to deal with masses that aren't changing their mass. So you could pull that m out and have this. Now here you're going to have to go from V1 to V2, and here you're going to have to go from T1 to T2. Can you get to here? Okay. Now this is going to be, when you integrate this, you're just going to get mv2 minus mv1. See, these really are vectors. And by Jove, we're done. Look, we've got the sum of all the impulses. I didn't put in these limits here, but I can. There they are. Is equal to the change in your momenta. The change in momenta. There you go. That's the impulse momentum equation. And we showed you where it came from. It came from Newton's second law. Okay. Well, let's work a problem then. Here we go. Any questions on that before we work a problem? Well, all right. I'm going to erase all that, but you're going to probably need that. So I need the room though. You can always look in your book, or you have it in your notes there. I was going to do problem 15.7. It looks pretty good. 15.7. Now let me see if I can find it. Hang on a second here. 15.7. It's on page 248. We have two crates, A and B. Here's A, and it's 100 pounds. And then there's B, it's a little smaller. It's 50 pounds. And they're on a surface. Come on now. They're on this surface, and the coefficient of kinetic friction is 0.25. Let me write that down. And somebody is pushing on it with a 50-pound force. Now, I like my forces in red. So there's that 50-pound force there. And now what are we supposed, in 5 seconds, what are we supposed to do? We're supposed to find their speed in 5 seconds. And the force exerted of crate A on crate B. All right, well, we'll do that. Now, I thought it'd be fun to do it with Newton's second law first and get the answers, and then to do it with impulse momentum and get the answers. Okay, now with Newton's second law, you know the drill. You have to put all the red stuff on there. Now, what we got here? We got 100 pounds doing this. 100 pounds. And then we have 100 pounds doing that. The normal force. 100 pounds. Now here you got 50 pounds. It's a little smaller. 50 pounds going down and 50 pounds going up. Yeah. And now we have friction. Now see, it's going to slide along here, and the friction on here will be 100 pounds times 0.25. That's 25 pounds. So we'll put it right here. We have a 25-pound friction there, and we have a 25. No. That'll be 0.25 times 50. That's 12.5 pounds, isn't it? Yeah. Yeah, you're going to have 12.5 pounds. Well, that's it. That's all your red stuff. And then as far as green stuff goes, we're just going to have a tangential unit vector going that way. And I don't know, you could put a normal unit vector here if it makes you happy. I don't think you need it. Come on now. Normal, there we go, normal unit vector going that way. It's kind of hard to put the normal unit vector because you always put it to the inside of a curve, but there's no curve. So I just stuck it on there. That'll do for now. Now let's use Newton's second law. Now, what they want us to find is the velocity after 5 seconds. Well, we'll get it. But using Newton's second law, the sum of the forces on this body, well, these cancel. That 100 and that 100 cancel. 50 and 50 cancel. It looks to me like we've got 50 going to the right. We're actually doing it in the tangential direction, aren't we? We got 50 pounds going to the right, minus 25 pounds going to the left, minus 12.5 pounds going to the left, equals the mass. I'm doing the whole thing here. The mass of the whole thing, watch it, it's got to be in slugs. If anybody needs me to, I'll explain slugs, but I've tried to before. And now I'm going to shut up for 1 minute, and I want you to find the acceleration of the two bodies. Go ahead, find the acceleration, then I'll call on somebody. If you tuned in late, we're right now we're doing problem 15.7. It's on page 248. And I'm going to call on one of my excellent students here. Let's pick on Jackson. Jackson, unmute and say hi. Hey, Jackson, did you get that acceleration yet?
Yeah, 2.683.
Yeah, that's what I got. I got an acceleration of I got 2.683. Is that what you said?
Yep.
Yeah, great. There's a whole bunch of threes there, but we won't sweat it. Now, Jackson, what are the units on that acceleration? I need the units.
6 tons. So it'd be feet per second squared.
There you go. Good.
Okay.
Good going. Proud of you. Now, they wanted to know the speed after 5 seconds. Well, here's the equation. V equals V sub O plus AT. You know what that is? That's a kinematic equation that we learned back in August. V sub O is 0. There is no initial. It starts at rest. We have the acceleration, and they said 5 seconds. So take this 2.6833 and multiply by 5 seconds, and we'll get the velocity. Here goes. I'm getting 13.41, a bunch of sixes, feet per second. Now let's see how we did. This was problem 15.7. I'm going to see what the answer book says, 15.7. It says 13.4 feet per second. The answer book rounded off. They got 13.4 feet per second. So we did great. We did great. But we use Newton's second law. See, this chapter here is on impulse momentum. Let's do this problem using that tool or that method. You get the same answer, but let's do it. Now this method here, you take the integral of f dt from, in this case, it'll be from 0 to 5 because they said 5 seconds, is equal to the mass times the final velocity minus 0, because see, it starts from rest, so the mass times the initial velocity is 0. And now just a minute, now I forgot something. There's a sigma in front of that. You have to add up all the impulses. You have to add up all the impulses. This term here is called impulse. This term here is called momentum. And we are using the impulse momentum equation. I'll tell you a little secret. If they give you time in a problem, if a problem includes the time, then you probably want to use the impulse momentum method. If they give you the distance involved, if they tell you how far a body pulley goes up and down or whatever, if they give you the distance, you probably want to use the work energy method. Now you understand that all these methods work, you get the same answer, it's just easier that way. Now, if they don't give you the time and they don't give you the distance, but they tell you about the forces, or you can get the forces, they give you the masses and gravity or whatever, then you'd want to use the Newton's second law method. There's just a little hint there to help you know what method should I use? Well, we're going to use two methods on this just to show you they all work, but it's easier if they give you the time to use the impulse momentum method. See, they gave us the time in this problem. They said the time is 5 seconds. Isn't that what they said? Let me read it. 5, yeah. See, they gave us the time. So this will be the easy way to do it. See, this is the impulse momentum method. We're going to do it. Here goes. All right. Well, this is the sum of all the impulses. So what I'm just going to do is I'm going to say 50 pounds minus the 25 pounds going the other way, minus the 12.5 pounds going to the left. That's the summation times the 5 seconds equals the mass. Well, the mass of the whole thing is, we have to have it in slugs, though. If anybody needs me to, I'll explain slugs. We've done it before, but I'll do stuff again if you need me to. See, if you do this, you'll get your slugs. That's the unit of mass in the American customary unit system, times the velocity. See, the mass times the velocity. Well, it'll be V2. There is no initial velocity. Okay, get your calculators. Plug all this stuff into your calculators and let's see what we get. Here we go. Well, I got an answer. When I plugged all that stuff in, I got 13.41, a bunch of sixes, feet per second. Wowie, that's the same answer we got using Newton's second law. See, we got this from Newton's second law. We got this one from impulse momentum. We could probably get this with work energy. And boy, it'd be the hard way, but wouldn't it be fun to do that? Wouldn't it be fun to do this problem with work energy? Probably wouldn't hurt us any. Let's do it that way. I need some room though. Why don't I make some room here? See, what I'm showing you is that we have these different methods. They all work. Some are just easier than others. Now, what is the work energy method? That's when they use the work energy theorem. The work energy theorem. And you know how that goes. It goes like this. The sum of all the works done on the body is equal to the change in kinetic energy of the body. That sounds familiar. That's the work energy theorem. Well, let's do that. Now, you see these 100 pounds, they don't do any work because the thing is moving perpendicular to them, and forces that are perpendicular to the motion don't do any work. See those 50 pounds? They don't do any work. I'll tell you what does work is that 50 pound times the distance it travels does work. You want to just call it maybe D for distance. The 100 pounds times the distance does work, but see, it's negative. It's negative work because the force, the motion is to the right, but the force is to the left. That gives you negative work. And then there's the 50 pounds times the distance you travel. It does negative work. And that's equal to the final minus the initial kinetic energy. It's equal to 1/2 the 150 over 32.2 V squared. Now here's the problem. We don't know what V is. Well, we do because we've solved it 2 other methods, but if you were doing this method, you don't know what the V is yet. And we don't know what the distance is. But see, they're related. They're related somehow. And here's a relationship. I think the distance traveled is the average velocity times the time. You guys know that. We know the time, it's 5 seconds. See, distance is velocity times the time. The trouble is, I think the velocity is changing here. See, it starts off at rest and it starts picking up speed. It's actually accelerating. But see, you could write this as 0 initial velocity plus your final velocity divided by 2. That'll give you the average. times 5 seconds. Ooh, we just came up with an equation that relates the distance traveled and the velocity, the final velocity of your bodies. You know what? We have 2 equations and 2 unknowns. Here, let me box them up for you. See, this is a little harder to do that with this method. You don't want to use this method, but it can be done. And let's do it, just so we can learn. Okay, so how would you do that? Well, see, take this equation here and write d like this. D is equal to 2.5 v. Can you get to here from here? Can you go d is equal to 5 over 2v? Yeah, 2.5 v. And see, then we could stick in, you see that d right there? We could stick in 2.5 v. We could stick in 2.5 v. And we could stick in 2.5 v. Now wait a minute, I've got a problem here. No, I don't. No, I don't. I don't have a problem. I think it'll work. I just need some room here. Let me. You don't need this stuff up here. Let me erase this so you can see what we got here. So here's what we got. We got 50 times 2.5d minus 100 times 2.5d minus, hey, you know what that 50 times 2.5, not 2.5, I mean v. Just about goofed up there. 2.5 v, and this is 100 times 2.5 v, and this is minus 50 times 2.5 v equals 1/2 150 over 32.2 v squared. Now we're going to do a little algebra trick now. You see that v squared? We're going to get rid of the square, and that gets rid of all these v's, doesn't it? And hey, we got a lovely equation with only one unknown. Put that in your calculators now. I'm going to shut up for a minute. Put that in your calculators, and let's see what v is. I got a crazy answer. I must have done something horribly wrong. No. This is wrong. This is wrong. You guys need to stay awake and help me here. When you solve for D, no, that's right. That's right, isn't it? Yeah, I think 2.5 v, 2.5 v, 2.5 v. Okay, well, let me. I'm getting a crazy answer. I'm doing something terribly wrong. Let me stare at this a while. Now, if you guys can figure out what I did wrong here, please speak up. We're trying to use the work energy theorem, which we shouldn't be doing because it's the hard way to do this problem. But it says the sum of the work done on this body those are the frictional forces, right? I think that's right. And what's the frictional force here? It's here's my problem right here, guys. This is my problem right here. That frictional force is not 100, it's 25. And I needed one of you guys. I need you guys. This is wrong. This should be 25. And this frictional force here is not 50, it's 12 and a half. 12 and a half. Okay. So now this is going to be 50 times 2.5 V, and this is going to be 25 times 2.5 V, and this is going to be 12 and a half times 2.5 V, and this is going to be 1/2 150 over 32.2 V squared. And we got rid of the squared and got rid of the V's. Now, put that in your calculator, and it's correct now. And find out what the velocity is. Go for it. I had the wrong numbers in there. Okay, I got my answer. Did you get 13.41, a bunch of sixes?
Yeah.
Yay! Hey, look at here. We got the same answer using work energy. We got the same answer using impulse momentum. And we got the same answer using Newton's second law, but I erased it. I had it here on the board, and I erased it. So now you know that you can solve these problems with any of these methods. You get the same answer, but some methods are easier to use than others. And the easiest one, if they give you the time, is the impulse momentum method. Okay, guys, please stay awake, because I made a mistake. I wrote down that the friction was 100 there, but the friction was 25. I wrote down the friction was 50, but the friction was 12 and a half. That's how come I couldn't get it right at first. Stay awake and help me. Okay, I'm going to erase all this. We're going to work another problem. But see, we got to review a little bit. We got to review Newton's second law, and we got to review work energy, didn't we? All right, well, I'm gonna say goodbye to that problem. That was problem 15.7. We got the same answer the answer book got. Only we did it 3 different ways. Okay, let's work another problem. All right, now this next one that I want to work, let's see here, until totally organized here. Let's do this one. This looks like fun. This is fundamental problem 15.6. Help me find it. 15.6. It's a fundamental problem. Yeah, I found it. It's on page 246. Page 246. They've got a 10-pound block. Let me draw the picture here. Oh, gee, come on now. We have a 10-pound block. 10-pound block. And it's got a cable here, goes over a pulley. And this goes down to a body B. That's a 10-pound block. And body B is an 8-pound block. And they said that they turned this thing loose, I guess from rest, maybe. And it attains a velocity of 1 foot per second in 5 seconds. So see, after 5 seconds, this will be down here someplace. Body B will be down here someplace, and it will be going 1 foot per second. Okay. It attains a velocity of 1 foot per second in 5 seconds. All right. Well, now they were talking about the 10-pound block, but wouldn't that be the same for both of them? If this one's going 1 foot per second after 5 seconds, this one would be going 1 foot per second after 5 seconds. They both have to go the same speed. They're tied together. So they both have the same speed. They both go the same distance. Now B is going down and A is going to the right. But they have to have the same velocity. Now they want to know the tension in the cord and the coefficient of kinetic friction. We're supposed to find the coefficient of kinetic friction and the tension in the cord. Neglect the weight of the pulley. Well, that's all the info they have. Okay. Well, again, now we could do this. You know what would really be fun is to do this all 3 ways with the Newton's second law and the work energy and the impulse momentum. Doesn't that sound like fun? I did not hear, oh, yes, Mr. Griffin. Yes, that sounds like fun. I didn't hear that. But I think it'd be good for us. I want you to master these tools, because when we get to solid bodies, you've got to have these tools mastered for particles. We're dealing with particles here. See, here's the difference. Particles don't spin. This thing just goes down, it doesn't spin. This block here just goes over to the right, it doesn't spin. But when we get to solid bodies, they can spin. And a solid body that spins has energy. And you have to account for that. Okay, well, they're giving you the time. Now, when they give you the time, which method should we use? I told you this, but I wonder if anybody listens to me. Braxton, unmute and say hello, please. Braxton.
Hi.
Hey, Braxton, if they give you the time, which method should you use? Should you use Newton's second law, work energy, or impulse momentum, Braxton? Which one?
I feel like you should use impulse momentum.
That is correct. If they give you the time, the easiest way to do a problem is with impulse momentum. Now, what'll be fun is we'll do it all 3 ways. We'll do it all 3 ways. But let's start with the impulse momentum. Now, the impulse momentum method we all know and love, or we're going to. It goes like this. I'll pick on Braxton again. Braxton, what do I put over here on the right side of that equation?
MV2 minus MV1.
You got it. He's got it. They call those things momenta. See, this is your final momentum, and that's your initial momentum. And they call this something too. That's called impulse. Another name for impulse is impact. Well, actually, there's a slight difference, but I'll tell you something about impact. One time, some drunk teenagers ran into a telephone pole. I don't know how fast they were going, but it was probably 45 miles an hour. And the front end of their car, they hit that telephone pole right perfect in the center. And the two headlights of their car were wrapped around that pole, and the headlights were looking at each other. Can you imagine the amount of force? Can you imagine the amount of force necessary to take the front end of that car and wrap it around that telephone pole where the lights, the headlights, are looking at each other? But see, here's the secret. This car is going at a speed, well, the initial speed of, say, 45 miles an hour. Now, the final speed is 0. Once it hits that telephone pole, the telephone pole does not give, okay? And the car stops. And the thing is, the time of the crash is very small. It sounds like this. Now that part is the tires on the pavement when the brakes are locked and the tires are screeching on the pavement and they're laying rubber. That's really not the crash. They're trying to stop. They've got the brake on and they're trying to stop. By the way, those teenagers were so drunk, I don't think they were permanently injured. They were so drunk and so loose. I think they survived. But here's the point. When you make this time teeny tiny, and that crash happens in a tiny fraction of a second, this force has to be very big. Do you understand? If this is small, this has got to be big, and that's your impact. That's your impulsive force, and they can be huge. Okay, well, let's do it. Well, wait a minute. What's the rules? You have to put the red stuff on there. So you got 8 pounds doing this. And you have 10 pounds doing this. And you have 10 pounds doing this. Now, I'm not even including the other pound, the other forces. See, if you wanted to, you could talk about the tension pulling on this and on this. This needs to be at 45 degrees. Let me rearrange that. There we go. That needs to be at 45 degrees because these have to be equal if it's a pulley. But I'm not really that concerned about those right now because, see, they're going to cancel out. Whatever this tension is in this cable is equal to the tension in that cable, but I'm not at all sure that it's equal to 8 pounds. I'm not sure that it's equal to 8 pounds. I'll have to think about that. But if you just look, whatever these are, though, they will cancel. If you look at the forces trying to move this thing, what you've got is you've got a frictional force. Did they ever tell you the friction? Oh, we don't know it. getting my lids mixed up. Okay, we have a frictional force. Doggone it, I need to put that in there. There we go. And there's your frictional force. I'm going to forget about these tensions, and I'm going to consider, I think I'm going to sneeze. Get that feeling. I'm going to consider, beware, it could happen anytime. I'm going to consider my system to be the two blocks and the cable. And so I don't need to consider internal forces like the tension in the cable. If you just considered the one block, that tension's external to it. Or if you just considered this 8-pound block, the tension there is external to it. But if you're considering the whole system of the two blocks, I don't think you have to consider the tension. So here's what you got for forces. You got 8 pounds making the thing go like that, minus the friction, which is mu sub k times your 10 pounds. Trouble is we don't know what mu sub k is. But that's it. And that's going to equal to the mass, which is, for the whole thing, is 18 pounds divided by 32.2 slugs times the final velocity. This is 0, I think. Does it start from rest? Let me read it. And block and velocities. Yeah, it starts from rest. Okay. Well, now we have a problem here. And wait a minute, I'm forgetting something. I'm forgetting my time. Let me squeeze that in. What'd they say, 5 seconds? Here we go, 5 seconds. Yeah, I squeezed it in. So you got to have the time in there. Okay, now let me read the problem. I'm missing something. It's yeah, we got the velocity. It's given. Look here, I'm going to circle it. It's 1. The velocity is given. It's 1. So you can put a 1 right in there. 1 foot per second. Hey, you can solve this for the kinetic coefficient. Do you understand? Here, let's put a 1 in there. 1 foot per second. Well, you have to go minus the mv1, but it's 0. It starts from rest. Okay, plug that in and solve. I'm going to shut up for a minute, and I want you to solve for the coefficient of kinetic friction. Here's your equation. We've got this lovely equation. Go for it. Solve that for, you don't need this term, it's 0. Solve that for the mu sub k. Go. Okay, now let me call on one of my excellent students here. Jackson. Jackson, unmute and say hello, please. Hey, Jackson. Did you get this mu sub k yet?
Yeah, double check. I think it's 0.788.
That's what I got. I got points.
Okay.
A bunch of 8s, looks like. Jackson, what are the units on that?
There are no units.
Man, that guy's sharp. See, I was trying to trick him there, but I couldn't trick Jackson on that. Okay, well, we got that. Well, so what? Let's see what else we're supposed to find here. Let's see. Determine, oh, we need the tension. Okay. Well, why don't we just look at one body at a time? Now, again, you can still use this same equation here. Let's do it. Here goes. We're going to do the sum of the forces, or sum of the impulses. But we're just going to do it on body A. All right, here goes. Now on body A, now here you have to include the tension. See, the tension, it's an external force on body A. You can't just forget it. So what you have there is tension minus the friction. But see, we can get the friction. You know what it is? It's 7.888 pounds. See, friction is mu sub k times the normal. The normal is 10 pounds. 10 times that's the friction. And now you have to multiply by the 5 seconds. Equals the mass. It's got to be in slugs. And running out of room here, I'll just put the velocity here, which we know is 1 foot per second. Okay, we got an equation, and there's only one unknown. Find the tension for me. Go ahead. Find the tension. Go. Well, I got a value for tension. Let me go to one of my excellent students here. Ashley, I don't think I've picked on you all morning, Ashley. Do you have the tension yet from here, Ashley?
7.95 pounds.
That's what I got. I got 7.95 pounds. Now, just to check it, let's do the same thing for body B. Now, see, on body B, you've got a tension. It's the same tension, but it's going up. So you have to, that's an external force on B. See, when you consider both bodies, you don't need to worry about the tensions. They cancel out, see, on both bodies. But on B, you got to include it. Okay, so do I have room to write that equation in here, maybe? Yeah, here we go. I'm writing the impulse momentum equation on B. Here it goes. Well, you got the 8 pounds minus the tension times 5 seconds, I think they said, right? 5 seconds, yeah, is equal to the mass. It's the 8 pounds. It's got to be in slugs, though. The unit of mass is slugs times your V minus, this is 0, it starts from rest. And we know what it is 1 foot per second. Okay, guys, plug this in and see what you get for the tension on body B. Go for it. Boy, Jove, I'm getting 7.95 pounds. Same answer we got before. Now, if you look in the back of the book to see how we did, this was problem 15.6. And they said mu sub k is 0.789. Now they said 0.789 in the book. They just rounded off. I think we did fine. And then F15.6, they said the tension, they said it's 7.95 pounds. Well, that's what we said. That's exactly what we said, 7.95 pounds. Hey, we did great. Now, we've got 3 minutes left, right? Oh, that's so sad. Have you ever noticed how time goes by so quickly when you're having fun? Now, if I had time, I would do this problem with Newton's second law and with work energy. I think we got time to do it with Newton's second law. Let me make some room here someplace. Some room over here. We might make it. Okay, Newton's second law. Well, some of the forces, Newton's second law is the sum of the forces equals ma. Now the thing is, they said it goes 1 foot per second, and it does it in 5 seconds. That's in the problem. If you read it, it says it attains the velocity of 1 foot per second in 5 seconds. Hey, we can get the acceleration. Isn't acceleration just velocity over time in this case? So I think the acceleration is 0.2 feet per second squared. Okay, great. So, hey, let's use that. How much time do I have? I have 1 minute. Here goes. Hey, let's just look at body B for a second. No, we need body A. Does that show up on? Yeah, that shows up. We're looking at body A, and see, well, the problem is I don't know what the tension is, do I? Using Newton's second law, but I know what I know what the acceleration is. Let's do the whole thing, A and B. A and B. So here's what you got. You've got 8 pounds trying to make the thing go, minus your mu sub k times 10 pounds. And that's it. And that's equal to 18 divided by 32.2 times 0.2. Look here. Here's an equation with only one unknown. You should be able to get mu sub k using Newton's second law. Oh gosh, I got 30 seconds left. Put that in your calculator. We know what the answer is supposed to be. See if it works. Let's see, 18 divided by 32.2 times 0.2 equals that. And then what do you do with it? I guess you subtract it from 8, huh? And then divide by 10. Boy, Jove, when I solve this for mu sub k, I get 0.788, bunch of 8s. We just found the coefficient of friction using Newton's second law. And if we had a little time, we could find the tension. And if we had more time, we could do this same problem with the work energy method. But we don't have it. Sad. Our time has come to an end. I hope you enjoyed it. I know I did. Any last comments? Because I've got my little cursor over this red box here. You better speak up. Well, goodbye,
good day.
students. Adios. We'll see
Bye.
you when? Monday at 9. No. Yeah, Monday at 9:30? Yeah. See you Monday 9:30. Adios, muchachos.